Just did it.
Excellent, thank you.
Sure thing.
All right, so welcome everyone to part two of chapter 15 on simulation for cohort one of the Effect Book Club. I'm going to attempt to get through uh, both the sort of use cases for simulation as well as power analysis today, and if we're lucky, we might be able to do some stuff about bootstrapping, but we shall see. So simulation is a really great tool in general, but it's particularly good for three different things: trying out new estimators that we haven't tried before, comparing different estimators, and testing what we need to break for an estimator to stop working, or essentially where can we violate assumptions. And the nice thing about simulations is that all of this can be done without writing proofs, so you don't have to do all the nitty-gritty math, which is great for somebody like me who is not adept at the nitty-gritty math. So we'll start off with the first of those, just trying out a new estimator. So we're going to start off with an example. Um, and this example is basically, we know that the standard error of a regression gets smaller as the variance of x gets bigger. Oh, sorry, let me just turn off do not disturb. So if the standard error of a regression gets smaller as the variance of x gets bigger, maybe if we limit our data to extreme values of x, the variance will get bigger and we'll get smaller standard errors. So what we can do is we can code this up. We can create a universe in which this is the case. So here we're going to do a data creation function where we can choose our own true effect. So we've got our function here, we choose the sample size, and we choose what the truth is, what our effect or our coefficient of x actually is in this example. So we run that function. We also have an estimation function, and this is where we decide how much of the data that we've created we're actually going to be keeping, given our sort of true relationship. So these are our two functions. We can take these together and we can run 1,000 simulations. So we'll go through 1 to 1,000. We will map our function or map our est model function with a sample size of 1,000. We'll keep 0.2% or 20% of the data, or keep the bottom and top 20%. That's what. And our true effect is 2. So in this, uh, true times x plus our norm, the true value is 2 here. And then we'll print the mean coefficient. So we've decided our true effect is 2. We get a mean coefficient of 1.99882, which is basically 2. Um, we can also print the standard deviation of this estimate, so 0.03, and the mean standard error, so 0.03. So our mean is almost exactly the same as the truth of 2. That's great. That is shows that we're not, creating a different mean. But what we're really interested in here is, are we actually going to get lower standard errors? And in order to do this, we actually have to compare estimators. So we have to compare an estimator where the data creation process is the same, but in one sample we'll keep all of the data, and in the other sample we're taking only the top and bottom 20%, like we did here. So that's the next sort of use case for simulation. So we take the exact same simulated data and then apply multiple different methods to it, allowing us to see which of these methods perform better. We can call this a horse race. You're basically taking uh, two methods and you are comparing them head to head. So we'll test the example that we just ran through against a vanilla regression. So we've got our estimated model function that we used before, and we've just modified it a little bit to have two different estimators. So first is the regular regression. So we've got a linear model where y is conditional on x, and we use our data frame. So very, very standard linear regression. And here we do the same linear regression, but we're filtering our data to keep only top and bottom quantiles. We'll then return all of our coefficients of the regressions. So the coefficients of model 1 and model 2 as a list, basically just to help us sort of extract the data, run 1,000 simulations just like we did the last time, stack all the results together in a data frame, and come up with a summary table. So this sum table comes from a package called vtable. So this is not in base R. You would have to install a package to get this particular output, but it's very handy. So if we take our vanilla regression on the top and our updated regression on the bottom, these are sort of basically what we got in the last section. So we have a mean of 2. They're exactly the same across the two. Great. But what we're interested in is the standard deviation. And it's actually larger with our updated analysis than it is with the vanilla regression. And that's not what we wanted. We were like, oh, what if we cut our data? Then maybe we can get a smaller standard error. And as expected, because this is all just like very known statistics, um, that's not what we get. So womp womp, we haven't found a magic answer to getting smaller standard errors in regression. The other thing that we can do with simulation is purposefully break things. So in statistical analysis, there are a lot of assumptions. These assumptions all need to be true in order to know for absolute certain what our estimators are doing. But even if we violate some of those assumptions and some of those assumptions are false, we might still be able to get a pretty good idea of what our estimators are doing. So we can use simulation to figure out which assumptions are okay to break and how many of them we can break without having a significant effect on our ability to get close to the truth. So to do this, what we're going to do is we're going to make a flexible data creation function that allows us to try different things. We then run our simulation with different data settings to see how this reflects the results. So instead of using the same data and comparing different ways to analyze that data like we did in the last little bit, we're actually creating slightly different data sets and running the same analysis to see how the slight differences in the data sets are affecting our results. One thing we should really be aware of when we're doing these types of simulations is that some assumptions are really sensitive to context. So we might run a simulation with a violated assumption and get a result that is still very close to the truth. And that is awesome, but it's always a good idea to run a simulation multiple times with data sets that do look different. Uh, because you might find a case where breaking that assumption actually really, really, really heavily impacts the results, and we don't want that. So what we're doing here is a kind of sensitivity analysis, basically asking how sensitive your your particular analysis is to changes in um, real life. Basically, the violations of assumptions that happen all of the time when you're analyzing data that, isn't simulated and isn't perfect. So here what we're going to do is we're going to expand the create data function that we've used in the previous examples and include another variable w. We're also going to put our iteration, so the sort of run this 1,000 times into its own function so that we can just do iteration a lot more easily. So we take our create data function, and we now have the effect of w on x and the effect of w on y. We create a tibble, we add the effect of wx times w, we add the effect of wx times w um, on both x and y basically, and then we return our data set. Our estimated model function is basically the same, it's just that we have different effects here. And we are doing just a very, very, very vanilla regression here. So just very similar or very simple linear regression. Next, what we do is we create a function for iteration. So we take our function that we have above, so the est model function, and we add an argument within that function called iters, and this is just how many iterations we're going to run for each run of this iterate function. So let's iterate this. We have our sample size of 2000. We have effects of 0 and an iteration of 200. So this should be unbiased because we have no effect of W. We can also test it with an effect of W on Y of 1. So this should still be unbiased. We can run an effect of uh, W on X of 1 plus our effect of W on Y of 1. And as we can see here, our results are starting to change. So we're getting essentially an effect of 0.5, whereas we had an effect of 0 up here. What about if we have a much milder effect or a much milder, yeah, effect of W on X and Y? There's still a change, but it's not huge. We can test whether it makes a difference if the effect is stronger on X or Y. We can test the inverse of that, Y on X. So this just really shows the flexibility of what we are doing, and we can basically take this iterate function, we can do whatever we want to it, and we can see just how messy things get if we violate our assumption. So those are the three things that power or simulation is very useful for. I'm getting ahead of myself because our next section is power analysis. So power analysis is one of the sort of really awesome use cases for simulation. Power analysis is basically the process of trying to figure out if the amount of firepower you have with your data is enough to detect whatever it is that you want to detect. It's commonly done with simulation, but there also exists out in the universe calculators and analytical methods specifically for performing power analysis. And the reason why we want power analysis is because many things can weaken statistical analysis and make us less likely to find the truth. Some of these include having really, really, or trying to find really, really small effects that can be difficult to find, working with data where we're interested in variation, but the variation itself is very small. This can make statistical analysis really tricky because statistical analysis is is basically driven by variation. That's essentially what we're looking at. It can be really difficult to pull signal from noise if you have a single effect of interest, but there are a lot of other effects that are going into this. Basically, anything where you're working with the real world is like this. Any study on humans, there's a lot of stuff that go on with humans, and any like ecological study, there are so many things that affect an environment. Uh, our statistical analyses can also be weak if we have really high standards. So if we really want small standard errors, we need more evidence to make up for those high standards. All of those problems, so these four problems here, can be fixed by increasing sample size. So a common use case of power analysis is to figure out exactly how big of a sample do we need in order to counteract these issues. Now, it can be really tempting to say like, oh, well, I have poor statistical power. Oh, well, like I might not find an effect if there is one. Why, but I should try anyways. Um, but that's not a good way to handle this because if you have poor statistical power, yes, you're not likely to find a significant effect if there is one in truth. But also, if you do find a significant effect, it's highly likely that that significant effect is a fluke, and there actually is not a significant effect in truth. So power analysis is like there's not really any cases where it's a bad idea, but it is particularly helpful in three cases. The first is that you're looking for a small effect or a part of a system where there's a lot of other stuff going on. The second is that you're looking to see how an effect varies across groups. So you're mostly interested in an interaction term. And this is because finding differences between groups is much more difficult than finding just the entire effect itself. And the third is when you're doing a randomized experiment, and this is just because you can actually control the sample size, so you might as well figure out what sample size you need to get tease apart the effect that you're interested in before you commit to running the study and recruiting um, study participants, for example. So power analysis is a way of balancing five different things. The first is the true effect size, so the coefficient in a regression, for example. The second is the amount of variation in the treatment, so the variation in X. The third is the amount of other variation in Y, so either the variation in Y just in general or the residual of a regression of Y on X. The fourth is the statistical precision. Or statistical power, which is the true positive rate, so how likely you are to get a positive when there actually is one. And the fifth is the sample size. And basically what we're doing anytime we run a power analysis is we are taking these uh, five traits of our analysis. We're holding four of them constant and um, figuring out what the fifth can be in order to achieve those other four of interest. So some common uses for power analysis are to get the minimum sample size we need for sufficient statistical power, get the minimum detectable effect under certain parameters. So how big of an effect does there have to be in real life in order for us to be able to actually see it and tease it out? And the statistical precision of our analysis or the true positive rate. So with statistical precision or statistical power, the more careful you are about false positives, the more likely you are to get a false negative. So the way I was sort of taught this is that there's a balancing act essentially between your statistical power and your alpha level or your p-value of interest. So if you do the standard um, alpha level of p is less than 0.05, then you will get, a particular statistical precision with your sort of data set and your analysis. And if you want to change one or the other, you can either increase your sample size or you can make compromises between the two. And that's sort of like that's a simplification, but that's that's how I was always sort of taught to think about it, at least in the context of the type of research that I do. So you can run a power analysis with any kind of statistical precision as a goal. Um, you could run this with standard errors, for example. So you might ask the question, what sample size do you need to make your standard errors below a certain value? Now, in order to do power analysis, you need to be able to fill in the values for 4 out of 5 of those pieces. So that power analysis can tell you the value you need for the fifth one. Um, we use standards for things like statistical power. You will say I want a statistical power of 80% or 90%. But with things like the amount of variation in the treatment or in Y or the true effect size, you're going to need to make educated guesses for these that are going to be very context specific. So these are going to be very specific to your data or your study system. And here you will want to um, you'll want to be consulting the literature. Have people done similar studies, but maybe not with your data? Or um, is there something that you can draw from other areas of knowledge for these systems? All right, so when coding a power analysis, in each iteration of the simulation, we need to be able to pull out a binary variable indicating whether the effect was statistically significant and return them. Once we have this binary variable um, of statistically significant or no across all of our iterations, the proportion that are significant is your statistical power. So if 45% of your iterations have a significant effect, then your statistical power is 45%. So it's actually very easy to sort of do the conversion of I do my simulation and then this is my statistical power. So here we do what we're very familiar with at this point. We create our data using a function that gives us our effect and um, our difference in effects between here, boys and girls. So we create our sample, a one standard deviation change in W makes treatment 10% less likely. So we've got a whole bunch of different things going on. We then do our model estimation. So we've got our dependent variable is test. We've got the likelihood of being a girl, the training, and our effective W here. And then we iterate this. So we have our number of iterations added on here. So we determine how much of the iteration we use. We then keep track of our progress by going if x is 100. So if we go up to 100, then we'll just print the result. All right. So what we want to do here is we want to find the minimum sample size. So we have our minimum sample size. We're going to run this. Sorry, I'm having a moment. Okay, yeah. So we are going to run this with a sample size of 10,000, 15,000, 20,000, and 25,000. We make a table of just those numbers just to so we know what our sample size was. And then we're going to use our iteration function up here to run this with a true effect of 2, the difference between boys and girls of zero point 0.8, and we'll run it 500 times. All right, so we run this um, on my computer. This took, I think, to do this and the minimum standard error, which is the next part. I think it took 30 seconds, 1 minute, something like that. So it wasn't very long, but it is something where it doesn't happen instantly, and this will get there will be more waiting involved the more complex your simulations become. So as you can see, we're running through our iterations here. So we do 100, 200, 300, 400, 500 over and over again. We're trying to find the first n with a power above 90%. And so here we have n, so we have our sample size, we have the power um, on the right. And so we see basically we need a sample size of 25,000 in order to get a power of over 90%. Now, what about our minimum detectable effect? So we can do the same thing here. We can test out a number of different effect sizes, basically do the exact same iteration. And what we find is that if we want uh, if we want a power of above 90%, our minimum detectable effect is going to be rather big, so it's going to be 3.2. So both of these are not super encouraging, and this would tell us that maybe this particular study isn't super feasible because we're either going to have huge effects or we're going to have a really, really, really big sample. Um, or I guess we're going to have both of those. So, maybe we might want to rethink this study. Are we actually going to be able to get 25,000 participants? I don't know. Maybe, maybe not. Okay, so we also have
Wait, actually, just a quick
yeah,
question.
yeah.
So I've never done this. And you said you have to keep 4 out of 5 constant. Have
Yeah.
you done this before? What would you play around with first? Because I mean, having a certain idea of how big the effect should be also interplays with how big your significance is going to be. So I think I'd be a bit overwhelmed in the beginning.
Yeah. I mean, I think in this case you if you're really unsure, you might want to do both. So you might want to be like, I am interested in a couple different effect sizes, and I'm also interested in a few different options for like sample size, and you might want to basically do crosses of those two. I haven't really done too much. I haven't really done simulation. I'm planning on doing it, so that's why I wanted to do this chapter, but I haven't actually sort of dug into the meat of it yet. But that's kind of how I would think about it is start to think about, like what are your different options for effect size based on the literature and how much data do you think you can get and test those? Because if you have a situation where, you can have, your lowest possible sample size and also still get enough power on your lowest possible or your lowest possible effect size. Yeah, low and low. Then that's great. That means your simulation tells you that like you should be golden, even if you're really conservative. Um, and I think being conservative is also a big thing. If you're uncertain, you kind of it kind of behooves you to go with the worst case scenario, um, and just say like, oh, if if the effects are really small, can I actually tease something out? There's also nothing to say that you can't do um, a post hoc analysis once you have collected the data and see and start to think about, how likely with the data you were collected you were to find a a true effect. I don't know, does that sort of make sense to everybody? Has anybody else actually run simulations, I guess is a question, because I have not.
Yeah, I've definitely run simulations, but not for the purposes of doing a power analysis.
Okay.
In my use case, it's I work in insurance. It's fitting a parametric model or something to simulate claims.
Hmm.
Yeah, my colleagues tend to just input their information, like you said, after the experiment or after designing the experiment into an app to get a sense of these numbers, but not necessarily go as deep as to run a simulation.
Yeah, gotcha. Yeah, because I guess like, one thing you could do with the power analysis is you can collect your data, you can say, okay, these are the results I had, but with the data I did have, maybe I would only be able to detect a huge effect size. So you can write that in your discussion and say this indicates that there's not a big effect, but more data needs to be collected in order to be able to determine if there are smaller effects at play. Something like that. Does that does that sort of help you think about it, Sarah?
Yes,
Okay.
definitely. Thank you. Because I was thinking of a colleague who has a super small sample size, like
Mm,
of 60 or so in 3 years. So it's like very low. And she was trying to figure out if it makes sense to continue with this project. So it's been trying to see how one could go about this. Yeah,
yeah,
thanks.
no problem. Also, coming from like biology and especially working with like museum specimens and fossils and things like that, it's like, sample size of 60 being small, how cute.
Yeah, but if you can't get the effect
Oh,
anyhow,
I
like
totally. Yeah, not to knock like wanting to be concerned about those things. It's just like for one of my PhD projects, I was like, I have a sample size of 20 and that's like huge.
So what do you do?
Cry a little bit. Do you mean what do I do like with such a small sample or like what was
Yes.
I looking at? Okay.
No, like how do you go about finding anything with such a small sample size?
A lot of it is just accepting that sometimes your ability to find true effects is going to be really limited. Um, this is part of the reason why I really want to do simulation and do simulation particularly for power analysis because it's not super commonly done um, in the field in which I did my PhD, and I'm I would like to sort of bring these analyses to sort of the types of research that we're doing and ask these questions, like, are we even actually able to detect effects? Um, and yeah, ultimately we're limited in that we really only can tease apart really big effects a lot of the time because the sample sizes are so small.
Yeah, makes sense to go sample the effects way then. Yeah.
Hmm. All right. So we'll see if we can get through the bootstrap thing in 20 minutes. The bootstrap section here is a little bit messier, so apologies. I was, as always, running out of time. It takes a really long time to make these slides, and I don't think I really um, accounted for that. But the next cohort will have something to work with, so that's great. So we've talked a little bit about bootstrapping before, and it's the process of repeating an analysis many times after sampling with replacement. So if you have an original data set of 1, 2, 3, and 4, then you could get bootstrap data sets like 3, 1, 1, 4 or 2, 4, 1, 4. And as you can see here, we're pulling numbers from the original data set multiple times. So, we have 2 1s here and 4 4s here when there's only one of each of those in the original data set. So the reason why we might want to use bootstrapping in the context of simulation is because one of the hardest parts about doing a simulation is figuring out how to create data that actually looks like it would in the real world. So we can do bootstrapping to just use real world data. That's really handy. Of course, this does have its downsides. So with a simulation, you're creating the data yourself. You know the true data generating process. That's not the case with bootstrapping. So you can't use bootstrapping to like check for bias in your estimate. You can see what your bootstrap simulated estimate is, but you don't know the true data generating process in order to compare that to. So this means that Bootstrap as a simulation tool is limited to cases where your question does not rely on comparing your results to the truth. And usually this means using Bootstrap to estimate standard errors, because by mimicking resampling, you're automatically simulating the interdependencies between the variables, and allowing any sort of oddities or strangeness in the true sampling distribution to become more apparent by basically bootstrap simulating stuff over and over and over again. So of course, standard errors aren't the only thing that bootstrapping is good for. Machine learning folks use bootstrapping for everything, not actually everything, but a lot of things, including using it to generate lots of training data sets. You can use Bootstrap to look at the variation of your model in a more general sense, like estimating a model, generating predicted values from that model, and then repeating so you can see how your predictions for each observation vary based on the sampling variation of the whole model. You can aggregate all simulated predictions together to get your actual prediction. There's a lot of fun stuff that you can do with bootstrapping. Now, if you're planning on using bootstrapping or your distribution from a bootstrap to do a hypothesis test, you want to first shift the distribution so it has the unbootstrapped estimate as the mean, before you compare the distribution to the null. And this actually produces the comparison that you're going for with a hypothesis test. Now, bootstrapping comes with its own set of assumptions, in order to provide good estimates of the standard error. Um, as is the bane of my existence, as we just sort of talked about, we need a reasonably large sample size. Um, we need to be sure that our data is at least somewhat well behaved. So if we have variables that follow really, really highly skewed distributions, Bootstrap might have difficulty. And we also need to be careful in accounting for how the observations might be related to each other. So here we're going to code a Bootstrap using the mtcars dataset. We create a function for resampling. So basically we're just slicing the sample and allowing for replacement. We can also do this more sort of by hand if we want to, but that's never fun. Automate everything. So we're going to create our bootstrap sample from here. Basically, we're just saying, okay, take this data set, mtcars, and make it bootstrap. So what we get here is all of our cars and all of our data, and I'm trying to see. Yeah, so as you can see here, we're getting the resampling with like this Mazda here. And there's our whole data set. Empty cars is also, fun fact, the bane of my existence because I know nothing about cars and it's used as an example so often that I'm like, I don't know what this is telling me. But that isn't me problem. So for all of these, we're going to need to specify an estimation function first. So unlike in our previous code examples, the estimation function is not going to call a data creation function. So before we kind of had our data creation nested within our estimation, we don't do that with the Bootstrap because we have a resampled data set. So we call that estimation function within our bootstrapping function. So this provides a bootstrap sample to be estimated, takes the estimates provided, and then sort of smushes them all together. All right, so we take our MT cars data set. We do an estimation function in which the first argument is the data, and the second is the indices defining the bootstrap sample. And we run our bootstrap call. So this will say bootstrap call, use the empty cars data, run our est_model function, and run the bootstrap 1,000 times. This results function here allows us to see both the coefficient estimates for our linear model up here. So the coefficient of like MPG, for example, and the bootstrap standard errors. So we can look at our results here. We've got ordinary non-parametric bootstrap using the boot function. You can see our original, our bias, and our standard area. So this is still very codey. So it's not actually that much easier than doing it by hand. But the benefit here is that using a purpose-built bootstrap command like boot comes with a lot of options that let you bootstrap in ways that are a bit more complex than simply sampling each observation with replacement, which is what you would essentially the only thing you'd be able to code by hand. And I didn't go over the by hand examples here, but they're in the book. They also provide ways of analyzing the distribution of outputs in different ways, like not just using the mean and standard deviation. You can also do bias correction, which is really handy. One of the ways that we do bias correction is called the BCA confidence intervals. So it looks at the proportion of times that a bootstrap estimate is lower than the non-bootstrapped estimate. If the distribution isn't skewed, this should be 50%. As well as the skew, it also looks at the skew of the distribution. Sorry, I like was copying and pasting here, so there's some stuff that's a little bit messy. So in R you can pass your results from boot, so the boot function that we used before, to a function called bootCI with the type as BCA to get a BCA confidence interval. So there are a number of variants of bootstrapping, and this is sort of what we were talking about with the utility of using a bootstrapping function instead of doing everything by hand, is you can very easily be like, okay, I want to use bootstrap variant X, I want to use bootstrap variant Y. So we've got something like the cluster bootstrap, which is a regular bootstrap, except instead of resampling individual observations, so a single row, you would resample clusters of observations known as blocks. This is really useful if you have hierarchical or panel data. Um, it can also be used in the context of time series data. Although with time series data, a cluster bootstrap is called a block bootstrap, just to make things confusing, even though they are essentially doing the same thing. When you're applying a cluster or block bootstrap to time series data, the time series is generally divided into blocks of continuous time. The blocks themselves are determined by one of several different uh, available algorithms for determining optimal block length. And then a common alternative to the block bootstrap is the moving block bootstrap, which instead of dividing the bootstrap into sort of discrete blocks of continuous time, it has a sliding window that gets resampled instead of splitting the data up. So you're getting overlap in the parts of the data set that you're collecting or that you're sampling from, whereas you don't get overlap in the block bootstrap. So this is just an example of a cluster bootstrap. And basically it's very similar to regular bootstrap, but it's also resampling. It's basically you're resampling from ID numbers rather than resampling from the entire data set. So you might have person number 34 four times in one bootstrap sampling and three times in another and once in another, rather than having like picking and choosing different observations that may or may not be from person 34. So here, the results from that would be, for example, a tibble where we have our X data set and we're getting person 1, person 3. We're getting X multiple times from person 3, so we've actually sampled person 3 twice here. Another popular type of bootstrap is residual resampling. So instead of resampling whole observations, you are resampling the residuals. So you perform your analysis using the original data, use your analysis to get a predicted outcome value, and also the residual, the difference between the actual outcome and the predicted outcome. Sorry, a bunch of these like little dudes didn't show up. You then perform bootstrap resampling to get resampled residuals. So you basically run your analysis, you get the residuals, and then you resample the residuals. So you might get certain residuals multiple times. And you create a new outcome variable by adding the residual to the actual outcome. So the idea here is that the predictors in your model never change with this process. So if there's correlation between predictors, so if they're interdependent, you are still getting that interdependence here. And that's just, still going to be reflected in your residuals. A downside of residual resampling is that it does not perform well if the errors are in any way related to the predictors. And this is an even stronger assumption for this type of bootstrap than the regular ordinary least squares regression assumption that errors are on average unrelated to predictors. There is also a bootstrap called the wild bootstrap, which is an extremely fun name. And it's really popular because it works under heteroscedasticity. even when we don't know the form that heteroscedasty takes. It can also perform well when the data is clustered, so it can work under sort of cases where we might use a cluster bootstrap. It actually outperforms the cluster bootstrap if the clusters are of different sizes, which may happen a lot in real world data. Like if you get dropouts from a study, although you might want to just like get rid of the dropouts depending on the study itself. So the cluster-based version of the wild bootstrap works better in cases where, if you had like a classroom of 100 kids and you're trying to compare or trying to include that in a sample with a classroom of 5 and a classroom of 10, things get really weird. Because the wild bootstrap is sort of very varied, if you want to use it, you will probably want to dig around to see how it applies to your particular type of data. There is an introduction by Martin in 2017 called The Wild Bootstrap in the Wiley Stats Ref.
I think I
And
looked at this recently, or
yeah,
tried to dig into some of the weeds here because he doesn't really go into details about it. And I
no.
think that reference is not freely available. Some of you folks might have it through your respective institutions, but
Oh yeah, classic Wiley. I almost certainly will have access to it. I'll look into it, and if I have it, I'll see if I can share it in the Slack maybe.
yeah, that would be cool. I
Yeah, no
appreciate it.
problem. And then if you do decide to implement the wild bootstrap, standard errors, you have to use different packages in order to implement them. So the sandwich package has vcove BS, which is a fun name, or or there are some options in the fwild cluster boot package. All right, so it's 10:57 and we actually managed to get through the entire chapter, so that's fun. I will put
Nice.
stop
Hey,
in the chapter.
one thing I want to post this reference that I found useful in terms
Awesome.
of what kind of bootstrap to employ. It doesn't, it's just like a 2-pager, not even. Because Ashley, you spoke about like the residual resampling versus resampling full cases. And there's also something called the parametric bootstrap as well.
Yeah,
Like if you had a linear regression, you could just sample random normals if you believe that your data is linearly related and your residuals are normally distributed. You can just kind of resample from that linear model. If you don't trust that your data is normally distributed, you can do the residual resampling. And then if you don't trust your model at all, like your linear model, you would probably want to do full case resampling. So it's really about like how much you trust your assumptions.
yeah,
Right. And so like if you're doing a full case resampling, you're going to get higher standard errors. So I would also assume that this stuff can kind of be gamed, right? Depending, like I want to see a significant result, so I'm going to use this parametric bootstrap or something like that. So you need to be careful with that. But anyway, I found this to be useful for some of the stuff that I've worked on.
yeah, yeah. It definitely seems useful. And yeah, I'm a little surprised that the book didn't talk about parametric bootstrapping because I feel like that's one that I've encountered in the wild a lot, um, without, necessarily knowing in depth about it.
Yep.
But, yeah. All right.
All
I'll put
right.